In this video, we're going to focus on calculating the entropy change for certain processes as it relates to physics. So let's start with this one. Calculate the entropy change of melting 15 grams of ice at 0 degrees Celsius. The entropy change, which is a measure of disorder, is equal to the heat transferred divided by the temperature. So to calculate the heat transferred in this example, it's equal to the mass times the latent heat of fusion. So the mass of ice is 15 grams. The latent heat of fusion is 334 joules per gram. And the temperature in Kelvin is 0 plus 273. So it's 273.15 Kelvin. So the entropy change for this process is 18.34 joules per Kelvin. So we can see that the unit grams cancel and it leaves behind joules per Kelvin. So that's the units for entropy, and that's it for this problem. Number 2, calculate the entropy change in heating 2 kilograms of water from 0 degrees Celsius to 100 degrees Celsius. And we're given a specific heat capacity of water. So how can we do this? Well, we can use the same formula. The entropy change is going to equal Q divided by T. But this time, we need to use an average temperature because the temperature is not constant. In the last example, when ice melts or when water freezes, the temperature is a constant 0 degrees Celsius or 273 Kelvin. In this case, the temperature changes from 0 to 100, so we need to use an average temperature. Now, the amount of heat energy that's required to heat up water, we can use this equation to calculate it. It's the mass times the specific heat capacity multiplied by the change in temperature. And so the mass in this example is 2 kilograms of water, and then the specific heat capacity is 4,184 joules per kilogram per Celsius. And the change in temperature, final minus initial, that's 100 minus 0, is 100 degrees Celsius. So we can see that the unit kilograms will cancel, and also Celsius will cancel. So now we need the average temperature. 0 degrees Celsius is approximately 273 Kelvin, and 100 degrees Celsius is 373 Kelvin. So if we average 273 and 373, if you add them up, divide by 2, the average temperature is 323 Kelvin, or if you want to be more precise, 323.15 Kelvin. So 2 times 4184 times 100 divided by 323.15. So that gives us this answer. The entropy change is going to be 2590 joules per Kelvin. And that's a rounded answer. Now, there's another more precise way of getting the answer. So you can use this formula to calculate the entropy change. It's equal to mc natural log of the final temperature divided by the initial temperature. So whenever you're heating up a substance, and if you wish to calculate the entropy change, this is the formula that you could use. So the mass is 2 kilograms, and then the specific heat capacity is 4184 joules per kilogram. Now you can write per Celsius or per Kelvin temperature. It works out the same way. And then it's going to be the natural log of the final temperature, which is 373, and this has to be in Kelvin, divided by the initial temperature of 273 Kelvin. And so this works out to be 2,612 joules per Kelvin. So we could say that the entropy change for this reaction is approximately 2600 joules per Kelvin. So that's a nice rounded value. But this answer is more precise. So this is another way in which you can calculate the entropy change when heating up a substance. 3 kilograms of water at 70 degrees Celsius is mixed with 3 kilograms of water at 30 degrees Celsius. And we're given the specific heat capacity of water. What is the final temperature of the mixture? So for both samples of water, the mass is the same and the specific heat capacity is the same. So the final temperature is simply going to be the average of 30 and 70. 30 plus 70 is 100, and 100 divided by 2 is 50. So the average temperature is 50. So let's focus on the hot water sample. The temperature is initially 70 degrees Celsius, and it's going to cool down to a final temperature of 50. So let's calculate the entropy change for that process. So we'll say delta SH for the hot water sample, and it's equal to Q divided by the average temperature, since the temperature is not constant. And so Q is equal to MCAT, MC delta T, and the mass is 3 kilograms. The specific heat capacity is 4184 joules per kilogram per Celsius, and the change in temperature, that's going to be final, which is 50 minus an initial of 70 divided by the average temperature. So if we average 70 and 50, 70 plus 50 is 120, 120 divided by 2 is 60, and then we need to convert that to Kelvin. So the average temperature is 60 degrees Celsius, and if we add 273 to that, that's going to be 333 Kelvin. So let's go ahead and plug this in. So 3 times 4184 times negative 20 divided by 333. So that's equal to negative 753.9 joules per Kelvin. So let's calculate the entropy change for the cold water sample. So for the cold water sample, it starts at 30 degrees Celsius and the temperature increases to 50. So the average temperature is going to be 30 plus 50, which is 80 divided by 2. So that's 40 degrees Celsius, and then we're going to add 273 to that number. So that's 313 Kelvin. Now let's calculate the entropy change. So it's going to be MC delta T. Well, first, it's Q over T. And Q is going to be MC delta T. And then we need to divide it by the average Kelvin temperature. So the mass, once again, is 3 kilograms. The specific heat capacity, 4184 joules per kilogram per Celsius. The final temperature is 50 minus the initial temperature of 30, divided by the average Kelvin temperature of 313. So this is going to be equal to positive 802 joules per Kelvin. So notice that for the cold water sample, the temperature is increasing. Anytime the temperature goes up, the entropy of the system will increase. So the entropy change is positive, as we could see in this example. For the hot water sample, the temperature decreased from 70 to 50, and so the entropy decreases as well. So the entropy change is negative, as we see in this example. So now we can calculate the total entropy change. So the total entropy change is simply going to be the sum of the two values that we have below. So that's going to be negative 753.9 plus 802. And so the net entropy change is 48.1 joules per kilogram. Joules per Kelvin. So that's the answer. Now let's use the other equation to get the same answer, the one that uses natural logs. So let's focus on this one. For the hot water sample, the temperature decreases from 70 to 50 degrees Celsius. So at 70 degrees Celsius, the Kelvin temperature is 343 Kelvin if you add 273 to it. And 50 plus 273 is 323 Kelvin. So delta S is going to be mc times the natural log of the final temperature divided by the initial temperature. So anytime you need to heat up a substance, you can calculate the entropy change using that formula. So the mass is 3 kilograms. The specific heat capacity is 4,184. And then it's going to be the natural log of the final temperature, which is 323 Kelvin, divided by the initial temperature of 343 Kelvin. And so this is equal to negative 754.1 joules per Kelvin. Now for the cold water sample, the temperature changes from 30 degrees Celsius to 50. So at 30, if you add 273, this is 303 Kelvin, and 50 is 323 Kelvin. So using this formula again, the entropy change for the cold water sample is going to be the mass, which is 3 times 4184 times the natural log of the final temperature, which is 323 Kelvin, divided by the initial Kelvin temperature of 303. And so this is going to be 802.3 joules per Kelvin. And this is positive because the temperature is increasing. So now to calculate delta S for the whole process, we need to add up these two values. So 802.3 plus negative 754.1, this is equal to 48.2 joules per Kelvin. So as we can see, these two answers are very close. Now let's talk about how we could derive the formula that helps us to calculate the entropy change whenever we heat up a substance from an initial temperature to a final temperature. So the entropy change is the difference between two entropy values, S2 minus S1. And we know that delta S is equal to Q divided by T. So it turns out that the entropy change is equal to the antiderivative from state 1 to state 2, dq divided by T, where dq is a small change in Q. Now Q is equal to mc delta T. So dq, a small change in Q, is going to be mc times a small change in temperature. So let's replace dq with that. So dq is going to be mc dt, which is what we have here, divided by the temperature T. Now mc is a constant, so I'm going to move that to the front. And now I have only temperature values in this expression. So this is going to be T1, the initial temperature, and T2, the final temperature. Now the antiderivative of 1 over x dx is the natural log of x. So the antiderivative of 1 over t is going to be the natural log of t, evaluated from the initial temperature to the final temperature. So we need to plug in the top one first. So this is going to be mc natural log t2 minus natural log t1. And ln A minus ln B is equivalent to ln A divided by B. So ln T2 minus ln T1 is equivalent to ln T2 over T1. So this is the formula to calculate the entropy change whenever you heat up a substance or if you cool down a substance. So anytime the temperature of a substance goes up, the entropy change is positive. The entropy increases. If the temperature of a substance goes down, the entropy change is negative. It decreases. So in this problem, we have a Carnot engine. So I'm going to draw an energy flow chart or energy flow diagram. And 12,000 joules of heat energy is absorbed from the hot reservoir, and the engine discards 6,000 joules of energy into the cold reservoir, which is at 300 Kelvin. Calculate the temperature of the hot reservoir. So we can use this formula. QH divided by QC is equal to TH divided by TC. Now QH, the heat energy that flows from the hot reservoir to the engine, that's 12,000. So this is the engine. So QH is 12,000 joules. QC, the absolute value of it, is 6,000 joules. QC itself is negative, but we're dealing with the absolute value in this equation. Our goal is to calculate TH, and TC is 300 Kelvin. So let's cross multiply. 12,000 times 300, that is 3,600,000, and that's equal to 6,000 times TH. So 3,600,000 divided by 6,000 is 600. So the temperature of the hot reservoir is 600 Kelvin. Now let's move on to part B. Determine the entropy change of the Carnot cycle. So first let's draw a PV diagram. And so the Carnot cycle looks something like this. That's a rough sketch. And let's call this A, B, C, and D. And so we have pressure on the y-axis, volume on the x-axis. Now as we go from position A to position B, this is an isothermal expansion. And so at this point, that's when heat energy is transferred from the hot reservoir to the engine. So thus we have QH, which is 12,000 joules. And the operating temperature, TH, that's 600 Kelvin. Now for the second step, going from B to C, that is an adiabatic expansion. And for an adiabatic expansion, Q is 0. And we know that delta S is Q divided by T. So if Q is 0, delta S is 0. So there is no entropy change for an adiabatic process. So we don't have to worry about going from B to C. Now going from C to D, that's an isothermal compression. And at that point, energy is released from the engine. So that's going to be QC. Now QC itself is negative 6,000 because heat is flowing out of the system. QH is positive 12,000 because heat is flowing into the system. So QH, which causes heat to flow into the system, that will increase the entropy of the system. But as heat flows out of the system, that will decrease the entropy of the system. Now because we have a cyclic process, the net entropy change should be 0, because the heat that flows into the system is equal to the total energy leaving the system. Keep in mind that this system does work, and the work is the difference between these two values. So the mechanical work is 6,000 joules. Now going back for the last part, from D to A, that is an adiabatic compression. And so Q is 0, which means the entropy change is 0. So we only need to focus on these two processes, the isothermal expansion and the isothermal compression to calculate the entropy change of the Carnot cycle. So for the isothermal expansion, we have delta SH when dealing with the hot reservoir. And for isothermal compression, we have delta SC when dealing with the cold reservoir in the engine. So S is Q divided by T. So this is going to be QH divided by TH plus QC divided by TC. So during isothermal expansion, the engine receives 12,000 joules of energy. So because energy is being absorbed, it's positive. Now we need to divide this by the operating temperature of the hot reservoir, which is 600 Kelvin. Now the engine loses 6,000 joules to the cold reservoir. Because it's losing thermal energy, QC is negative. And TC, that's 300 Kelvin. That's the operating temperature of the cold reservoir. So if we take 12,000 and divide it by 600, the entropy change for receiving heat energy from the hot reservoir, that's going to be positive 20 joules per Kelvin. And if we take negative 6,000 divided by 300, that's going to be negative 20 joules per Kelvin. So for an ideal heat engine, such as the Carnot engine, the entropy change for a reversible cyclic process is 0. And so that's it for this video. Thanks for watching.